Okay, so in this particular video, we'll do an extension of the video I did titled Projectile Motion _2. It uses the same animation, but I've asked different parts here just to show you how to attack it in case you're asked to perform. All right, so same animation here. Here's the cannon that is shooting a cannonball with a vertical velocity of 60, also a horizontal velocity of 60 as indicated in the animation. Okay, so if you haven't seen the previous video, I highly suggest you do so. All right, so let's go ahead and do A, B, C, D, and E, and I'll show you how to attack this using different strategies, and hopefully you pick the quickest one to get there. All right, so let's do it. So in this slide, I'll do part A and B. Okay, so part A asks us to calculate the maximum height relative to the launch position. So here in this diagram, I have a visual for you. It says relative to the launch position. So therefore, I'm just going to measure everything relative to where the cannon is. So I just drew a horizontal line across, and I just drew a vertical line that meets the vertex of the trajectory. All right, so I'll call that hmax. You can call it ymax if you want. It doesn't really matter. So let's calculate A. In order to calculate A, I think the easiest way to do it is using this particular kinematics function that does not involve time. For one reason, you know that at the peak of the flight, VFY must be 0. The component in the vertical direction approaches 0, and the only thing that is left at the peak. So if you watch the animation where my cursor is, that vertical arrow goes to 0 at the peak. So I'll use that point, and I'll use this function because it's easiest to do. Okay, so therefore VFY square is 0 because VFY is 0. So I'm going to go ahead and cancel it out. And then really the function simplified down to just negative VIY square over 2G. Well, we know what VIY is. VIY is given to us in the animation as 60. So if you watch my cursor where it resets, at times equal to 0, there it is. It was 60. And then G, we already know, and this is to use G again as negative 10 meters per second squared, just for the sake of whole numbers and simplification. All right. So therefore, I can just plug in VIY as 60 meters per second. I'm going to square that. I carry down the negative sign because the negative sign is part of the function. And then here's 2 times parentheses negative 10 meters per second square. And if you simplify all that, you should get 180 meters. Okay, so the maximum height that it reaches during this particular animation is 180 meters up. All right, so let's do that. So that's part A for you. And part B asks you to find the velocity at 3.5 seconds. So it's good to note that the velocity changes throughout the flight. Why? Because if you look at the animation, the horizontal component, Vx, stays the same, but Vy keeps changing. So every time you find velocity, you have to do Pythagorean theorem, but essentially the vertical, aka the vertical leg of the triangle, keeps shrinking as it approaches peak, so therefore the velocity keeps changing. All right, so it's important to keep those concepts in mind. All right, so let's go ahead and do part B. To find the velocity at 3.5 seconds, I need to know a couple of things, Vx and Vy at that specific time, at 3.5 seconds. Well, this one's pretty easy. I know what Vx is. Vx is 60 because it stays constant throughout the whole entire flight. What I don't know is I don't know what my velocity is in the vertical direction. So V of t here in the y direction. So I need to figure that out. But that's not too bad. We can just use this particular function. Average acceleration is equal to Vfy minus Viy over change in time. So you notice here I've used subscripts y here just so that you're not confused with which velocity to use. There's Vfx, Vfy, and there's Vf. And since I'm using acceleration due to gravity, which is in the vertical direction, my velocities that I'm using must be in the vertical direction as well. So hence the subscript y here. All right. So therefore, I can just isolate for this function and solve for Vfy. Well, I need to solve for Vfy at 3.5 seconds. I know G, I know T is 3.5 seconds, and I know my VIY is 60. So really here it's just plug and chug. Okay. Here, gravity is negative 10, time is 3.5, VIY is 60. So if I simplify this on my calculator, you should get a value of 25 meters per second. So from here, we can just substitute in for wherever our vertical velocity is at 3.5 seconds. And then really, that's it. Okay. So just square both of the terms on the right, add them together, and then square root it. So if you square them and then sum them up, you should get 4,225. And then this is VT square but to get vt by itself, you have to square root both sides. So therefore, square rooting vt squared, which is give us vt, and then square rooting the sum of this stuff here will give us 65 meters per second. Now, since it asks for velocity, velocity is a vector, so you do need to provide a direction. So you notice here, I have my direction as 22.6 degrees northeast. Now, in case you don't know how to find the 22.6 degrees northeast because you haven't watched the other video, watch the top right of my screen. So essentially, I know two pieces of information. I know Vx is 60 meters per second at 3.5 seconds. I just found Vy at 3.5 seconds, which is 25 meters per second. So this is my hypotenuse. That vector there, the magnitude of it, we just calculated, which is 65. But to find the angle, it's this angle right here. Well, to find this angle, I can simply just do tangent, which is just opposite over adjacent. So if you do tangent, you should get a value of 22.6 degrees. So theta here is equal to inverse tan, which is opposite over adjacent. Opposite is 25. Your adjacent leg here is 60. So if you do that, it is 22.6 degrees, and the direction is northeast because this vector is pointing to the right and up. Okay, so that's that for part B. All right, let's do C and D. Part C says the time required to reach a height of 120 meters above launch position. So this one's not too bad. So here, I'm just going to use our kinematics equation that says delta y equals VIYT plus 1/2 GT squared. I know my VIY is 60. I know my G is -10. And really, all we have to do is do a little basic manipulation and use quadratic here. So delta y, I substitute in 420 because the problem, or part C, says you want to find the time that it takes to reach 120 meters above where it was launched. So delta y is 120. It's positive because it's on its way up. Okay, and then VIY is 60 because it's given it in the animation. At times you go to 0. The vertical velocity VY was 60. T is your unknown. G here, I just substituted for -10 because it asks us to use -10. And then T here is just unknown, so I'll keep that T squared as is. So hopefully by now, if you've watched my other videos, I like to use quadratic for this particular step. Why? Because I have a T square, I have a T, and then I have some sort of coefficient on the left side. So I can set the whole function equal to 0. So by doing so, I need to move this positive 120 over to the right side of the function, which makes it -120. And then I'm just going to rearrange it so that it looks like it's in the quadratic format. So I'm just going to write the T squared term first. Okay, so 1/2 times -10 is -5 T squared. So that's the highest exponent, so I'll write -5T squared. The next term is the term with the T, which is 60T. Here's 60T. And then the 120, or the -120, is the term without the coefficient. So therefore, let me just, I left the units out here, so let me just fix this real quick. Okay, I'll just be consistent here, and I'll just erase that M right there, because I just need the coefficients. Okay, all right. So therefore, if you do quadratic, you should get a value of 2.54 and 9.46. So I'll just exit my screen and I'll just do the quadratic solver on the internet. All right. So here we have our A is -5, B is 60, and C is -120. So -5, 60, and -120. Let me see. Oh, excuse me. Where'd it go? Oh, that's most. Okay. So if you do -5 for A, and you do positive 60, and if you do -120, hopefully you have a quadratic solver in your graphing calculator. If not, these types of problems will take you a while. All right, so if I do that, and as you can see, my x here is 2.535, which I rounded to about 2.54, and then the other value is 9.46. So as you can see, having a quadratic solver on your calculator is super, super useful. So that's how those values came about, okay? All right, so let's do it. All right, so let me just hide this, okay? Therefore, that is the answer to C. So there are two values where it reaches a height of 120 meters above, because it's going to go up, hit 120, but on its way down, it'll hit 120 again. All right, let's do part D. Part D asks us to determine the cannonball speed. So really here, just find the velocity, but don't find the angle because it just said speed when it has traveled 288 meters horizontally. So here, because it asks for speed, we can just use the same strategy as we did in the early part of this video. Use Pythagorean theorem. V square equals Vx squared plus Vy squared at that specific time or distance. But here, we already know Vx again because Vx is 60 and it stays constant, but we don't know what V of t is, okay? So how fast is it moving after it has traveled 288 meters horizontally? I don't know, but we can find it real quick. So in order to find V, we need to use this function. V is equal to gt plus VIY. We know what g is. We know VIY, but we don't know how much time. Okay, so you notice here now you're going to run into another issue where, well, you use a different function, but then you don't know what the time is, which is fine. But you do know that it traveled 288 meters horizontally. You know that Vx is 60. So therefore, if you use your kinematics equation for the displacement in the horizontal direction, you actually have two given variables here, delta x, which is 288. Vx is 60, so the only thing unknown here is your t. So I'm just going to go ahead and do that. Okay, so 288 meters equals to 60 meters per second times time. If I solve for time, I will get a value of 4.8. Well, this 4.8 seconds, I can plug it back in here now to find what my V is at 4.8 seconds or at 288 meters horizontally. So if I do that, if I carry my work down here, okay, you should get, again, the negative 10 I just carried down. Instead of t, I substituted t for 4.8, and then the 60 I just carried down. And then if you do that on your calculator, you should get a value of 12 meters per second. Okay. Now, well, what do I do with 12 meters per second? This is the velocity after it has traveled 288 meters to the right. So this is the vertical component. So you notice here it says VFY. It's not VF, it's VFY. So I just found that VFY is 12 meters per second. So I can substitute that in from my Pythagorean theorem. The 60 in the first term gets carried down. V of t at 288 meters horizontally is 12 meters per second. So therefore, if I do Pythagorean theorem, I'll get this. Sum up the right side, I'll get 3,744. And then I still need to square root it because this is V of t squared. I just need V of t, so I'll radical both sides. If you do that, you should get a value of 61.2. And I don't need the direction because it asks for speed. So I'm done here. Okay. Now let's do part E. Part E is similar to part C. It asks you for what time or times here. You know, will the cannonball be at a height of 150? I'm going to show you how to do this using a couple different strategies. Again, I will defer to using quadratic. So if you don't have a quadratic function or solver on your calculator, you're going to make a easy task into a really time-consuming task because I will not do quadratic by hand. It's just tedious at this point in your academic career. All right. So it says height of 150. Therefore, I can replace delta y with 150. VIY is 60 at times equal to 0. My t is my unknown. G, I plug a negative 10. So if you kept up with part C, this is just a rerun of this, except for a different height. Okay. Therefore, I want to, again, set the whole function equal to 0, moving this positive 150 to the right side, which makes it negative 150. And if I do that, I want to rearrange the terms so it looks like the negative 5 is in the front, and then the 60, and then next is the 150. You can ignore that meters, or here, I'll just delete it. Excuse me. It doesn't interfere with your math, but I left all the units again. Okay. And then from here, you can rearrange it. So here, your A coefficient is negative 5, your C is 60, and then your A is negative 5, your B is 60, and your C is negative 150. Okay, so if you do that on your quadratic solver, you should get these two values, 3.55 and 8.45. All right, so I'm going to exit the screen and just, again, punch it into the quadratic solver on the internet and then show you that it does come out to be the same. Okay, so negative 5, 60, and negative 150. So here's my quadratic solver. So the only thing difference here is the C coefficient. I'm going to punch that in. And there are your two values of 3.55 and 8.45. And so find a calculator that can do this or graph it or use a graphing calculator. Okay, let's do it. Oh, excuse me, go back. Okay. Now, if you don't like this strategy or you don't know how to do quadratic, the other strategy is to kind of do it the long way. Okay. Well, to find time, you can use the average acceleration equation. Here, I just flip-flop acceleration in t. So to find time, you take VFY minus VIY over G. You notice here my V's in the numerator is VFY and VIY because this is G, so I'm focusing my attention on just the vertical direction. I don't know what my VFY is, okay, because it says reach 150 meters. So I don't know what my VFY is. I know my VI is 60. I know G is negative 10 meters per second square, but that's okay. You can find VFY using this particular function, okay. VFY square minus VIY square equals 2G delta Y. So here you have everything. You know VIY, you know G, you know delta Y, which is given in the statement in part E. So if you isolate for VFY square, you can just simply move this negative VI y squared term to the right, and then we just plug in values here. I'm gonna leave the units out just because I'm running out of space on the screen. Here's the 2, G is negative 10, Y is positive 150, VIY is positive 60. I'm gonna square that. So if you simplify all the stuff on the right side, you get 600. But then this is VFY square. So therefore, to find VFY, just square root both sides as we've been doing this whole video. Therefore, VFY is 24.5 meters per second. Now that I know what VFY is at 150 meters vertically, I can substitute that in for VFY here. Okay, so VFY is now 24.5 meters per second. I'll subtract that from 60. A small number minus a big number will give us a negative number. So it'll be negative 35.5 divided by negative 10, which leaves us with a time of 3.55 seconds, which is the same as it is on the left side of the screen here. So I like quadratic. It gets my job done quicker, but if you want to take this long route just because you don't know how to do quadratic or you don't have a calculator that performs quadratic, it'll eat up more time. So I encourage you, find a graphing calculator, graph it, pull out these information quickly. All right, so conceptually, so that gives us the first answer of 3.55 seconds. Well, what about the 8.45 seconds, right? Well, the 8.45 seconds can come just from a little bit of deduction. Okay, so here we just found that, watch this image on the top right here. We just found, okay, so I have that black line because I know it hits 150 at 2 different points in time. Okay, so again, on its way up at 150, it'll keep rising to higher height, and then on the way down, it'll hit 150 meters again. So those 2 dots just represents the 150 meters above launch position. So here, this bracket we just found, it took 3.55 seconds to hit the first 150 meter mark vertically. But I know that it took 6 seconds, to reach peak because Vy is 60, gravity is negative 10, so it will take 6 seconds to get to the peak. So therefore, the second bracket is 2.45 because 3.55 plus 2.45 is 6 seconds. Well, due to symmetry, this next bracket that came up is also 2.45. So if it's going to take 2.45 seconds from this dot, this black dot, to get to the peak, it'll also take 2.45 seconds from the peak down to that same vertical position. So if you sum all these values up, 3.55, 2.48, 2.45, and another 2.45, you will get 8.45 seconds, which makes sense. So if you watch my cursor, it's going to take 3.55 seconds to hit the first, and it's going to keep going. That'll take an additional 2.45 seconds, and it'll take an additional 2.45 seconds to fall down to that same vertical position, which is 150 meters there. Okay, so if you add all those up, you'll get the other answer that's boxed on the left side. I like the left side, you do you. Okay, stay nerdy, don't be whack.